Okay, so now let's describe formally this conversion algorithm from NFA to DFA. Okay, so first let's recall some notations that would be useful for us. So an NFA is defined by the regular tuples notations, where hopefully you remember what each one means. For our purposes, let's recall the transition function delta star that work on strings. And the important thing to remember is that we had all this nonsense about the epsilon reach, which was really what was very painful, because the epsilon reach, we had to apply it before and after every transition, so things got a bit messy, but we got the following recursive definition, which essentially we are going to emulate in the construction. Okay, so this is recall one. The second thing you have to recall is a string is accepted by an NFA if the set of states that it might be in after handling an input string W contained one of the accept states. Okay, and the language of the automata, of course, is just the set of all strings that are accepted. Okay, so now we can describe the algorithm. So you give me, so the input is an NFA N, and we want to build a DFA D that is equivalent to it. So the set of states of the DFA is going to be the power set of the states, right? All possible subsets. The start state of the new automata S star is just going to be the epsilon reach of S, right? So S is the start set of the NFA, but we need to do the epsilon reach in case that it can reach many more states because of the epsilon transition. To remind you, the epsilon reach is just all the set of all the reachable states from this state, which is of course also equivalent to delta star of S of epsilon. The state of the set of states that are accept state in the new DFA is, well, all the subsets of the set of states such that they contain an accept state of the original NFA. And the transition function is the what you would expect, right? So if you're given a state configuration X and an input character A, what you do, you just compute for every state in X, you compute the transition on A using the transition function of N. To remind you, a transition function for N, which is an NFA, is a set of states. So this is a union of set of states, so everything is fine, right? Because this returns us a set of states of the original NFA, which is of course just a configuration. So this indeed shows us how to move from X on A to some other configuration. Okay, so this is the construction. Here is an example. We start with this this NFA, right? And we immediately and this is the resulting DFA, where again the start state is Q0, Q1 because there is an epsilon transition, right? So you would think that the start state would be only Q0, but because there is an epsilon transition, it's going to be both Q0 and Q1, and the rest just follows as as it was described. Okay, so that's that. I guess the only interesting thing here to observe, so let's see what's the interesting thing here, is that Q0 it can be in only in the beginning, right? Because once you read the input character, it can no longer be in the set of states. So that implies that right, so in fact on 0 and 1, sorry. Okay, so maybe I should do the reduction in more detail. Okay, so this is the start configuration, Q0, Q1. Let's assume that you get 1, right? So if you get the 1, you can move from Q0 to Q2, but then you abandon Q1, right? And of course, if you get to Q2, you can of course also go to Q3 because there's an epsilon transition. So indeed, you move into this state, right? If you're in Q2, Q3, and you get 0, 1, you know, Q3, if you get any input, you immediately go to hell, namely the set of states become empty. And I guess this is the only one that is left to explain. Q0, Q1, and you get 0, right? So if you get 0, then you move to Q3, right? You move to Q3, and those two states die, and that's it, right? So that's why you get the DFA on the right. And again, this is a situation where, you know, things get tedious and you really want a computer to do it, not do it manually by hand. But we are where we are. Okay. So as we've seen in the examples already, it's helpful to not just compute all the configuration because the number is exponential. So an easy optimization that is worth using is that you figure out what's the start configuration, right? You essentially take the start state, compute its epsilon reach. That gives you a set of states, which is the start configuration. And then you start building the automata by exploring locally from this configuration, right? You see, you compute the transition of this configuration to other configurations, and you keep exploring, right? You do some kind of a BFS or DFS, whatever, on this graph configuration, where, you know, you compute the configuration only if you reached it at some point. So that makes the generated automatas smaller in practice and easier to understand what's going on. Okay. Right. Okay, so the only non-trivial thing maybe to see about this algorithm is that, okay, we start with the start configuration, right? And now we need to compute the transition, right? So to this end, we have to compute this union of transitions, right? For every state in the configuration X, we need to compute this union on the transition function. And this we just do in 3 steps, right? You compute the epsilon reach of the state Q, then you compute the transition itself, right? For all the states in this, and then you take the epsilon reach of this set, right? So you do it in 3 steps. And now the resulting set of states, you get U, right? I guess that should not be U, that should be, oh no, it's U, this one, right? Sorry, I'm using 2 different notations. If U is a new configuration that was not explored before, then we add it to the queue of configuration yet to be explored, and we continue in this fashion until the queue is empty, right? A regular DFS or BFS algorithm. So we explore this graph of configuration, starting with the start configuration, so we don't have to construct parts that are not relevant. So this is the construction algorithm. What remains is to prove that this construction algorithm is correct, which would be our next stop.